Assalamualaikum and good afternoon to all. I hope everyone is in good health. Thank you very much for joining us in the KPPIM International Webinar 2023 on Mathematical Sciences, Session 4. Your presence is our happiness. My name is Muhammad Saiful Ahmad Shah, P. Azlan Shah, and I am the moderator for Session 4. Before we start, let's recite Surah Al-Fatiha. Alhamdulillah. Praise and thanks to Allah. We meet again in the first session. For your information, one of the purposes of having this hybrid webinar is to provide a platform for academicians, students, and researchers to share and promote their latest research and views in the fields of mathematics, statistics, and natural science with others. With a tagline, #Boost Our Visibility. There are 13 sections throughout the year 2023, in which for each session, we will have two speakers from Uzbekistan, India, and Indonesia, as well as, of course, speaker from UiTM Malaysia. Without further ado, please let me introduce the first speaker for our first session, Dr. Nur Izzati Khairudin. Dr. Izzati is a senior lecturer at University Technology Mara, UiTM Cawangan Perlis, Kampus Arau, Malaysia. She obtained her Master in Mathematics and Bachelor in Mathematics from the School of Mathematical Sciences, University Science Malaysia, USM. She has a PhD from University Science Malaysia, USM, specializing in mathematical modeling with a focus on dissipative solitons, solitary wave, dynamic, and analysis. Please welcome Dr. Izzati to give a 30-minute talk on her topic, the fixed points of the complex Swift-Hohenberg equation, and a 10-minute question and answer session. Give a big applause to our first speaker.
All right. Thank you. Thank you, Saiful. Okay, let me share my slide. Okay. All right. So I hope that everyone can see. Okay, this is my first slide. So can I start now, Saiful? Okay.
Sorry, Dr. Izzati.
Yeah.
We cannot hear your voice.
Oh, cannot. Oh, yeah. We start first. Mute speaker. Okay, right now, can you hear?
Problem with voice? Dr. Hazwani? We don't have any problem with voice. Something with your computer.
Dr. Izzati.
Yeah. Oh. Okay, how about Dr. Azwani? Can you hear my voice? Can you hear? So far, so good, cannot. I think my setting already got speaker and then microphone.
I think the problem with Dr. Hazwani's PC. I can hear. Susanna.
So can I proceed or okay?
Sure, Dr. Izzati, you can proceed now.
Okay, proceed. Okay, so let me share. Share again. Where is it? Okay, myself. Okay, so I hope that everyone please sit tight and chillax because of today is Friday's afternoon. So so when it comes to Friday's afternoon, so a bit when waiting for 5 p.m. to go back from work. Okay, so not heavy, but this is my research. Okay, the fixed point of complex Swift-Hohenberg equation. And my name is Dr. Nur Izzati Khairudin. You can call me Izzati from School of Mathematical Sciences, College of Computing, Informatics and Media, UiTM Perlis branch. Okay, so this is my outline. Okay, talk about abstract. Okay, then talk about solitons in general. Like to introduce to everyone about dissociative solitons in general, and then I go into my research, fixed points of a complex Swift-Hohenberg equation, and the last one is about future recommendation. So my intention is to be speaker for today. I'd like to introduce about dissociative solitons in general because of dissociative solitons in Malaysia still at early stage. So I hope that who knows, everyone who watching right now or listening right now may be interested with my field. Okay, so we can, you know, make a discussion or we can do something about it later. Okay, so this is my abstract. Okay, we like to conduct a study to examine the stability of fixed point in the complex Swift-Hohenberg equation, in short, CSHE, by using a modified variational approach. Okay, we also like to analyze the fixed point as we employed Euler-Lagrange equations, and we discovered the eigenvalues of the Jacobian matrix reach the imaginary axis, which indicate the occurrence of half bifurcation. So to the presence of a stable pulse solution in this system was also found to be influenced by trial functions, the nonlinear gain, epsilon, and the linear loss parameter delta. So then we like to investigate the behavior of stable soliton solutions as we varied a bifurcation parameter epsilon and also delta. So before we go into further, so I like to introduce you guys about solitons. So what's the solitons? Solitons can be considered as self-localized solution as a nonlinear partial PDE. So it started from John Scott Russell in 1834. A bit history there. Observed a general solution of a certain class of equation that called waves of translation. It is actually come from his experiment in the tunnel, not in tunnel, in canal, if I'm not mistaken. And then he make a wave. Okay, and then from wave, he translate into waves of translation. So, and then later in 1965, Zabriskie and Kraskell introduced or coined the term soliton when studying numerical solution of the KdV equation. Then later, okay, in 1990s, a dramatic point occurred. Okay, because of when you see here, many physicists understood the limitation of the soliton theory. Why? Because of in 1990s, at that time, that's the beginning of technology. So everyone, you know, evolve with technology, and as the technology goes on, as the time goes on, so the technology become more complicated. So when the technology become more complicated and the real world application problems become more complex, so as same goes to equation. So the equation at that time only limit to soliton theory, so it's not suit, it's not aligned with the better. I'm sorry, with the complexness of real world situation at that time. So because of that limitation, the theory had to be extended just to cover localized solutions in conservative Hamiltonian system. And then they like to construct a theory of soliton system with loss and gain. And then later they come up with new term, solitary pulse or dissociative soliton in cases with gain and loss. So after all that history, they begin with dissociative solitons, DS. Okay, it means dissociative solitons mean solitons in dissociative system. So talk about dissociative system lah. So what means solitons in dissociative system? Means that have an infinite number of degrees of freedom. So what the meaning of infinite number of degrees of freedom? It means that you can produce a countless number of soliton solutions with a countless number of bifurcation. So there's so many solutions when they talk about dissociative system, right? So and then we go to dissociative soliton again. Okay, to talk about a localized structure which exists for an extended period of time, even though parts of the structure experience gain and loss of energy or mass. Okay, so maybe example can be like structure could be a profile of light intensity, temperature, magnetic field, and then talk about dissociative solitons. it has two, for now, it has two mathematical model. First is cubic quintic complex Gisbert-Landat equation, or short CGLE, and another one is complex Swift-Hohenberg equation, CSHE. Okay, so all of these two mathematical models can be applied into optical communication systems and fiber lasers. And this is I'd like to show to you guys about the first the first mathematical model is CGLE. Okay, number one. So the difference between CGLE and CSHE here. Okay, CSHE, which that I studied CSHE when I was in my PhD. So this one, the difference is the order of the differential. So this one for CGLE, it has two order, but for CSHE it had fourth order. So and then for CSHE it has eight parameters, while CGLE it has 6 parameters. So the longer equation, it has more parameters. Okay, so that's about CSHE. So this one is the interpretation in terms of parameter from CSHE. Okay, then now we go to the concept. Okay, why and how distributive solitons built. Okay, so the first one is actually the fundamental extension for solitons in integrable and Hamiltonian system. Then three principles that contribute to distributive solitons. First is classic soliton theory. Second is nonlinear dynamics. Talk about theory of applications, and the last one is Prigoghine's ideas of self-organization. So we go to the first principle, which is classic soliton theory. The first one is just extended from integrable system and then extend to Hamiltonian system, and then because of right now we are dealing with a complicated real world situation. So this distributive system it is extend from Hamiltonian system, but Hamiltonian system still relevant. But it has a limit, certain limit lah. So that's why this system have been introduced to the world lah. Okay, so then the balance between dispersion and nonlinearity. Okay, because of from this balance, it creates stationary localized solution, and then also it adding the balance between gain and loss. So it makes soliton to be stationary object because of those two balance between nonlinearity and also dispersion, and another one the balance between gain and loss. So it called a two parameter family, and the soliton solution are the result of double balance. So means double balance here from the two parameter family between the balance between gain and loss, and also the balance between dispersion and nonlinearity. So this is the figure I would like to show you to everyone. Okay, so the difference between Hamiltonian system in one boundary, or in one, for example, like in one wave. So what it has, so from Hamiltonian system, it has dispersion and nonlinearity only. So different with a differentiative system, it has two parameter family, dispersion and nonlinearity, and also gain and loss. So it create more soliton solution. Okay, create more limit, create more and more soliton solution. Okay, so now we go for nonlinear dynamics. Okay, so this is the second concept of this soliton. So a soliton as we think, or we describe the soliton as a fixed point of an infinite dimensional dynamical system. So what's the fixed point? Okay, it comes from parameters fixed, a period of pulsation fixed, shapes at particular point of period fixed. So means it's not everything fixed, but when it comes to fixed point, our intention is we like to describe the behavior of the solitons, would like to be pulsating. From stationary, it tends to be pulsating. So when you have a pulsating solitons, so it comes from fixed point lah. So then stability of fixed point actually determine the stability of the soliton itself. So that's why we need to find the stability. We just not find fixed point only, but we need to find the stability of the fixed point because when we play with a system, we need to look at the stability of that system itself. So the transformation into limit cycle according to system parameter. So then changing a class of this soliton solution according to its bifurcation. So it go back to the stability of fixed point. So this is the figure, like to say the bone of solitons. So solitons, we go to Hamiltonian system. Okay, when you go to Hamiltonian system, it's actually admit only stationary soliton. However, if you go to different system, it's actually admit countless of behavior of soliton solution. For example, it can admit to positive soliton, and then after positive soliton, it can extend to another behavior which is called creeping soliton or erupting soliton, and also plane positing soliton. So we will look at the like to say the characteristic or the shape of each positing solitons. So after this, okay, so this one about nonlinear dynamics. Okay, still talk about stationary soliton, and then what is stationary solitons? It also can be pulses or front, where that shows the overall gain and loss must be balanced. If not balanced, it could be something else. Okay, then later, how about positing solitons? Soliton is a limit cycle, and then this actually exists in certain range of equation parameters, and eventually anomaly very quickly converge to another class of positing solitons. For example, like erupting or chaotic. And with small changes in the parameter, it actually can change something else in the state in the system. So this one lah, okay, bifurcation is a system as generally from fixed point can transform further in can be to chaotic solitons, or from fixed point can transform to limit cycle, where the limit cycle, when you look at the behavior, it's actually to pulsation lah. Then this one, classes of positive soliton. Here the shape, or like to say the result or the graph or the soliton itself, if you convert from positing into something else, or based on if you change some parameter vary. For example, like this, from positive soliton, if you change certain parameters, it can be creeping soliton. So this one lah, like this. So about erupting, from positing to erupting, it look like this, and then positing to plane positing, it more flat. You don't have the peak for the erupting and creeping. It has a little bit peak there at the front, and then you see for the plane positing at the tail, at the end it will be flat. So it's different lah for each soliton. Okay, so then this one is another example of positing solitons of the CGLE. This one is called a plane positing soliton, and this one is called period doubling. And it can go further. Okay, for example, like exploding soliton, it looks like this. Okay, why it called exploding? Because of at the tail, it looks like stationary, but at the middle part, it not just one explode, but only it can be two exploding, or two explosion, or three explosion or more. So this one, you can call it as an exploding soliton. So then this one can be a chaotic soliton. It looks like this. And about snaking soliton also, you can describe it like this. It's similar like period doubling, but it has more shape than period doubling. So because of it has more shape than period doubling, so we call it as a snaking soliton, and it also look like snake trying to move forward, something like that. So then still about nonlinear dynamics, the second concept of diffuse soliton, a large variety of soliton profile. So not only snaking soliton, not only positive soliton, so it actually can form rope waves. And another one is spiny solitons, where the appearance of sharp peaks on top of a more stable, wider soliton. So these two is the latest soliton that have been produced for, if I'm not mistaken, Archimedes and Mankas in last 2 years or last year. So this one is kind of like a bit unstable in terms of its shape. So this one is Prigogine ideas of self-organization. It means the third concept of the S, which is solitons. So the theory of system far for equilibrium means that soliton, a self-organized formation requiring a continuous supply of energy and matter, or both. They need both to live. Okay, in simple term, self-organization means that for a given set of external parameters, certain initial condition converge to stable localized solution of the system. Thus, the final state actually determined by physical laws, not by the initial condition. So we look at the result, yes, everyone does, but at the end, we need to look back at the fundamental part of the soliton. So we have boundary condition, initial condition, and parameter value. All of this we need to look at so that the concept of soliton still hold on, still at the, still, I don't know what to say, but still better. Okay, so then can I continue? So this one is Prigogine ideas of self-organization, still a third concept. So the majority of process in nature are governed by far more complicated dynamics because of we dealing with complex equation, complex PDE. So then stationary solutions can be considerably more involved. And then usually if you do this research, and you definitely get stationary solution. Then extend the concept to highly complicated objects, for example, like animal species and the formation of life itself. So when you talk about this is soliton applied to animal, or this is soliton applied to human or living, for example, human or animal. So it become more complicated, and we not just focus on wave, but we need to focus on matter because of or mass, something like that. So there's so many things need to be considered if you further or extend this soliton into animal or human living. So this one just summary of what happened to diffuse solitons. Okay, so we have if you look at the A figure A, the concept of solitons have three: classic soliton theory, nonlinear dynamics theory of bifurcation, and Prigogine's ideas of self-organization. All three contribute to concept of solitons. And another one is I would like to share about the balance of two parameter family, loss and gain, and nonlinearity and dispersion. So now I'd like to go further into my research about fixed point of complex Swift-Hohenberg equation. So I already showed to you guys about Cauchy, the equation of Cauchy. So what can we do? What can we do with the Cauchy? Okay, so actually what we did, study deals with infinite dimensional system. And then the motivation why we like to study the fixed point, because of the fact that Cauchy has only formed one class of pulse or stationary solution. And then also Soto Crespo and Archimedes stated that Cauchy has positing soliton similar to CGLE. Thus, it deserves careful study for this type of solution. And then the positing soliton exists at an equal level with stationary solutions, where it demonstrates the possibility of dynamics in this system. So at the end, why we like to do this as summary, because of we like to have Cauchy to produce positing soliton, not only stationary soliton. So yeah, and then in 2016, Yoboi et al. Applied a method for Cauchy called an alternative variational semi-analytical method. And then the motivation to this problem shows the effort was not enough to show the bifurcation in the Cauchy. So then later becomes our motivation to study whether the system can converge into limit cycles. And then there is possibility of positing soliton bifurcated using the Cauchy, since the equation is transformation from the CGLE, complex Lisenburg Lambda equation. And then we like to investigate on the existence of its wide class of soliton solution in distributive system. It means that I would like to to further all that theory, all the motivations to make sure that Cixi can have positing soliton. So we need to touch the fixed point first. So then what we did, analyzing the stability of fixed point through Euler-Lagrange Cixi equations using the modified variational formulation. So then when I talk about modified variational formulation, need to have trial function. So these two trial function been chosen and then been inspired from Archimedes and Mancas. So this one, equation 3 and 4. And then later, because of its a variational, modified variational formulation, it need to have Lagrangian for the complex Swift-Hohenberg equation. So this one, equation number 2. And then we substitute the trial function 3 and 4 into equation number 2. Then we get the average Lagrangian, this one, equation number 6. And then later, we vary the new average Lagrangian, equation number 6, previous slide, with respect to A naught, alpha, and sigma. Okay, so this one we're following Euler-Lagrange equation, equation number 7, and the last, equation number 8 and equation number 10, equation 8 until 10, sorry, Euler-Lagrange equations, sorry, not dispersionless. This one is another another research. So please cut the dispersionless. All right. So a question for the Cixi for this one is A naught, alpha, and also sigma. So then after we get the equation number 8 and until equation number 10, so all of this not only called Euler-Lagrange equation. So it also can be described as a fixed point lah, but we need to find what's the number of fixed point here. So before we go further, so we need to choose 2 parameter or 1 parameter, but right now we chose 2 parameter, which nonlinear gain and the linear loss parameter, because we like to study the effect of the system. And then it's due to nonlinear gain, this one, the epsilon governs the existence of fixed point, and delta, the linear loss, provide the perfect balance between losses and gains in the system. So that's the motivation why we touch 2 parameters there. So then after that, the stability of the fixed point actually determined from the analysis of the Jacobian eigenvalue. This is there's not the formula, but you need to find the determinant by using I used here that, okay, determinant lambda I3 means that it has a 3 by 3 matrix minus with Jacobian. So the corresponding values for the parameter are like this, I stated here. And then later, after in Mathematica do the works, the eigenvalues of Jacobian matrix are like this in equation 12 and equation 13. So if you look here for equation 12, okay, there has a negative real number and also complex number there. So what we can talk about equation number 12 and equation number 13, 2 Jacobian eigenvalues are complex conjugate and has negative real part. So 3 equations correspond to be a stable focus as the real part of Jacobian eigenvalues is negative. So based on theory of verification, the S there shows 1 pair of complex eigenvalues appear. So bifurcation for a system, there's so many system here of fixed point 8 until 10 were not occurred because of the Euler-Lagrange equation not correspond to periodic solution. So we have big picture here where the stability shows that 1 pair of complex eigenvalue. It means that the Cixi, when we apply into a variational formulation, so we will not get positing soliton. So we will maybe we will get stationary soliton. So a bit contradict there with our motivation. But before we conclude that is actually contradict with our motivation, we need to analyze the behavior. So now the findings of stationary soliton. Okay, we study the effect by vary 2 parameters, nonlinear gain and then the linear loss by integrating equations 8 until 10 numerically for different set of various system parameters. and then perform numerical simulation using Runge-Kutta fourth order method with step size X and Z 0.1. So why we choose 0.1? Because of the 4 decimal place accuracy was already achieved. So that's why we we choose 0.1. So this one, the corresponding values of parameter and also the fixed point that we get. And then we take the fixed point here as their initial condition. So then the stationary soliton evaluated 8 from equation 8 until 10 and trial function with parameter epsilon and delta when we vary epsilon and delta, and then later let's try to vary the epsilon. So we get here like this from figure A until D, and the last one when epsilon is negative 0.2, something like this. Okay, so what we can conclude, we actually get new derivative effect for C-Shi, which is that stationary solitons. Although it's common in this soliton, in this solitons world. Okay, if you have stationary solitons, it's common lah that the solution. However, still since we focusing on C-Shi, so it's make a new discovery, although that it's just stationary soliton. So then it reveals that the peak output of amplitude A at its highest peak when the value epsilon is negative 0.2, and then the factor that developing the stationary soliton, first the choices of parameters, and then second the system essentially depended on 2 parameter family, and then the third, the linear loss dissipation term does not destroy the pulse and necessary condition for existence of stable pulse. So the big picture or the big summary that we can tell you that there is no occurrence of the periodicity of the solution in the C-Shi, since eigenvalues play one of the major roles in constructing behavior of derivative solitons in the system. So then future recommendation, we can go into nonlinear transmission line, NLT, because of it's a trend right now starting 2021, because of NLTs is paving the way for accurate modeling of electrical soliton, and then go for human being. Okay, then we need to put a matter into our derivative solitons, because of from cell and then you extend to organ and then you extend to animal, so it's also considered as derivative soliton. So we need to do this research, especially when we talk about animal or human. It's a bit challenging because of it's complicated. It's more complicated than fiber lasers or communication, something like that. So then, and the last one is talk about brain waves, mathematical element, put thermodynamics and electrical signal. So right now I'm pursuing brain waves, mathematical DS employed in brain waves. But when we talk about brain waves, it's also complicated. I think that every research in this world is complicated. But when we talk about brain wave, so when we talk about brain, so it's unique. So it's related with derivative solitons and also electrical signal. So when we talk about electrical signal, we go back to NLT. So I hope that everyone clear with my presentation, and because I'm a bit nervous actually, so pardon with my presentation, and I hope that everyone satisfied with my presentation for today. So thank you, and back to Saiful.
Thank you for sharing your interesting insight with us, Dr. Izzati. Now we will open our question and answer session. If anyone has any question regarding the topic that has presented just now, please feel free to comment down below or just unmute yourself and ask the question or give any suggestion.
May I ask a question, please?
Yes.
All right, Dr. Izzati,
Yeah.
I want to look at this all in a mathematical point of view. So you have two differential equations.
Yeah.
As I understood, solutions to that two differential equations, or some of solutions I understood, are called solitons. Am I
Yeah,
right?
that's
Am I right or not?
yeah, you're right.
Okay. So you are studying fixed points of equations or solutions to that differential equations. The first thing. Another thing is, what does it mean, fixed point? Fixed point means you should act by something that something is moving. So that's why some points are fixed. So you should
Yes,
do,
that's true. Yeah,
yeah.
that's the fixed point in terms of these solitons.
Yeah.
Because of
So let me finish. Then so you have so you have some operator. So that means you acting to solutions, your solitons, by some operator. Is it possible to show that action first? Then once you formulate action of some operator, then it will be a mathematical problem. So you can solve that mathematical problem and formulate your problem in terms of mathematics to solve it. That will be a moment, because you are talking about many things, but hardly all of them are related to mathematics. You're just you talked on some applications of your research or something else. But in terms of mathematics, you should do. Can you give some such kind more mathematical formulation of your problem? Thank you.
Okay, so I think that I cannot remember all your question, but
Last one is important.
okay, I try to answer all your questions. Okay, about the first one, if I'm not mistaken, about fixed point, isn't it? So about fixed point, yeah, that's true. Because of that fixed point, we in distributive solitons world, when we talk about fixed point, okay, it's not. It's actually we're trying to find positive solitons. So a fixed point there, it actually help us to
Sorry,
create
fixed with respect to what?
fixed point. Fixed
No.
point, and when we talk about bifurcation,
I
so
know that. What does it mean, fixed point? So your point is moving. So
yeah,
so
moving.
you're finding some fixed point with respect to action, some operator. So that I'm interested in. So what is the operator, and what kind point you are taking to move under the action of that operator?
What do you mean by operator here? Is it
No,
parameter?
because what does it mean? You want to move some points, right, on the solution. Or yeah, you can say you changing solution. Solution has some parameters. So taking that parameters, you call them points. Then you are looking for points, fixed points under that operator. So that's why I'm just trying to understand in this point of view, your research.
So if you look here about fixed point, is actually when you parameter, it means that fixed parameters fixed, and then period of position fixed, and then everything must be fixed. Means that you fix, let's say you have 8 parameters, and then you want to vary 2 parameters. So and then you need to take 6 parameters have to be fixed, and then when you talk about bifurcation, so the fixed point usually it moves spiral, right? So it moves spiral. So we take that point, but we need to consider the Euler-Lagrange equation, A naught, alpha naught, and also sigma naught. So all that we consider it as a fixed point. And then all the fixed point, when they reach A naught, alpha naught, and sigma naught, then we take it as an initial condition so that we can do numerical simulation for diffusive soliton or for CSHI lah, complex Swift-Hohenberg equation.
Okay, so you mentioned Lagrangian. So how
Yeah.
that Lagrangian effect to that? How where you are using Lagrangian to for that to find the fixed points?
Okay, so all that in terms of numerical simulation. So we're not trying to, because of we trying, this is PDE. So in terms of PDE, it's produce approximate solution. So it's hard to find analytical solution. So when it comes to approximate solution, the best thing is we do a numerical simulation lah. So before we find Lagrangian equation, so we use chosen trial function, and then this chosen trial function we apply into a complex surface equation, and then by using this one, the Lagrangian, okay, so we do differentiation and everything, and then we'll get the average Lagrangian. So this one lah, okay, by using this expression, and then later after that we get average Lagrangian. Because of based on the trial function, we have three trial parameter, A naught, alpha, and sigma. So then we break it down into three lah, something like this. This one is the mathematical part of my research. A naught here, and then a sigma, and also alpha and sigma. So this one is a mathematical part lah. So this one also I actually not use when I still remember when I was in my PhD years. All this I try to derive by myself without using using Mathematica or any kind of programming lah, because of I still remember my co-supervisor, he said that it's good for me to practice my derivation not using using the help from Mathematica or MATLAB, some sort like that. So I think that this is the mathematical part that I think that you said you asked before lah, I think. And then
say regarding Lagrangian, I want to know. Say, do you have such a criterion? We have fixed point if and only if Lagrangian has this property. Do you have such kind of criterion or not?
pardon? Can you repeat the question?
Because you mentioned Lagrangian
Yeah.
related to your research in a fixed point. Do you have such a criterion like this? Say, point is fixed. We have fixed point if and only if Lagrangian has this property. So
Oh, no,
that will be more and less mathematical approach.
Okay, I try to.
Do we have that kind of criterion?
Oh no, we don't have that, because of we focus on more simulation in Mathematica. So what we do here, because of it, we're dealing with complex surface equation. We're dealing with fourth order equation. So it's already complex. So what we do, we try to break it down from PDE into ODE. So that because of ODE, and then we try to simple our way in terms of in finding behavior of safety soliton. So we don't have that the criterion that what you're looking for. So and then one thing is we like to find the behavior. Our motivation is trying to prove that this Sishi can produce positing. So we not ignore the mathematical part. We still have the mathematical part, but the criterion that you asking for about the criterion of fixed point there, you don't have that. But
Because roughly speaking, you are numerically solving that two differential equations.
no, only one different.
No, I mean, no, it doesn't matter. Okay, so focus on one. So you are trying to solve numerically that the differential equations, right?
Yeah,
I
that's
see.
right.
So then trying to looking at that numerical solution, then try to areas or just cases when the solution has the fixed point or not, something like this.
Yes,
But
because
you are no, I'm interested in the following, because you have differential equation. Differential equation has parameters.
that's
And once you solve differential equations, that parameters come to that solution. So now, if you change parameters, then of course you will change the differential equation. In a differential equation first. If you change parameters in the solution, then again you will get another action. So first action is on differential equation, another action and in solution. In the solution. So which one you are studying? In action on the solution of that differential equation, solving them numerically, or just for differential equation itself?
Oh, okay. So I take it the solution, I take it the parameter and then change into the solution. The result of the result is what I'm talking about is the Euler-Lagrange equation. The three, A naught, the A, the alpha, and also the sigma. So from there, I fix the 6 parameters and 2 I vary. So then later we get then we use simulation and then we get the behavior.
Okay, thank you.
Okay.
We also have a question here. So let me read the question. So first on slide 40, how do you choose the corresponding values of the parameters? Is
Which
there any
ones?
conditions of the value?
Cypher, which slide?
This 40.
This 40. This one, is it? This one, girl? This one?
40. This one 43.
43. 40.
Yeah, 40.
This one, tak nampak lah pula, sekejap. Is it?
Yeah, this one.
This one, this slide.
Yeah.
Oh, you choose this one.
Yeah.
Okay. Do you mean that how I find the result for a lambda?
Sorry, 39.
39. This one.
Yeah, parameter.
Oh, okay. So this one just not inspired. I take it from Archimedes and Mencas. So I take it from them, and then because of and then why they list that beta, betul, and then H, everything, like for example, like H equivalent to 0.05. So everything here that's stated here has a reason. So for example, like sigma or H, okay, so they make what call the parameter analysis, parameter range, and then they take from the parameter range, they took out the most stable one. So that's why they get for example, like H equivalent to 0.5, something like that, because of the parameter range that they make. So far, so good.
Thank you for letting me. Okay, is there any question? I take it as no. So thank you, Dr. Izzati.
Okay, most welcome.
Moving on to our next speaker is Dr. Aziza A. Akbarova, who will Dr. Aziza A. Akbarova is a lecturer at Karachi State University, Uzbekistan. She obtained her PhD in Physical and Mathematical Sciences from the National University of Uzbekistan, named after Mirza Ulugh. Her PhD research specialized in the area of computational and discrete mathematics. Please welcome Dr. Aziza A. Akbarova, who will give a 30-minute talk on her presentation entitled Numerical Solution of the System of Saint-Venant Equation, and a 10 minutes for a question and answer session. Give a big applause to our second speaker.
It's equations day, I see.
Hello. Hello, dear participants of the webinar, international webinar. I am Akbarova Aziza, and I am lecturer at the Karachi State University. And today my talk is devoted about 1 minute, please. Okay. It's okay?
Yeah, we can see.
See my
You can-
presentation?
yeah. You can proceed.
Yes.
Yes, okay. And my presentation is about the numerical solution of the system of Saint-Venant equations, and this report will be submitted in this order. This report plan: introduction, preliminary information, difference splitting scheme, and numerical example, and conclusion. And the behavior of water on rivers and small rivers, lakes, oceans, as well as smaller bodies of water was first described by the equation of Saint-Venant. Ademar Jean-Claude Barré de Saint-Venant wrote down the equation for unsteady one-dimensional fluid motion known as the Saint-Venant equation in 1871, and the desire to understand and curb the behavior of water has been with mankind since ancient times. With the development of science, mankind has made big steps forward in this area, but to this day, the problem of unsteady movement of open stream remains an urgent problem. This problem includes such important problems as the problem of floods of rivers and the problem of daily and weekly regulation of the productivity of hydropower plants, and the problem of during break a dam break, and the problem of the floods. And Saint-Venant equations are often used in theoretical and applied studies, and study of unsteady water flow of an upper channel. Therefore, we consider it expedient to pay attention to computational experiment of Saint-Venant equations. To the study of the property of unsteady flow of an open flows described by the system of Saint-Venant equation has been studied of many local and foreign scientists. For example, Abdurrahimov, Muzaffarov, Lutiev in the article "The Movement of Water in Open Channel." The channel's derivation of the hypothetical Saint-Venant equation from the Navier-Stokes equation is given based on the levels of conservation of momentum and mass of liquid. And other scientists as Muzaev and Turayeva offer two methods for solving the initial boundary value problem for the Saint-Venant equation, which is described in the article in the Vladikavkaz Scientific Journal. Next, scientists in the Semechin cites a work called Analysis of the System of Equation of Saint-Venant by analytical and numerical methods, where the differential equation of conservation diffusion is studied, and which follow from the system of equation of Saint-Venant, which describes the unsteady movement of water in the riverbed. And in the Scientific Journal of Hydraulic Research published in an article High Resolution and Non-Acceleration Solution of Saint-Venant Equation in Non-Rectangular and Non-Prismatic Channel by Brett et F. Sanders. The paper presents a scheme for modeling the flow around the open channels in the wet and dry layers in non-rectangular and non-prismatic channel. And next, and in the work Starodumov, the one-dimensional differential Saint-Venant models and its kinematic approximation are considered. and describing the free movement of water in an open channel. For the kinematic approximation, which is a first order quasi-linear equation, in the stationary case, this is a general analytical solution. And in the work, Abubakar, Diagne, and Miroslav Kristiks, the problem of stabilization of two-layer Saint-Venant model is considered, which is a coupled system of two convective partial differential equation with the right and two convection of the left in the proof of stability. The authors used the Lyapunov function, and which is necessary to determine the parameter. Next, scientists and Vinsong Lai and offer computational eventually hybrid finite volume difference method for numerical solving Saint-Venant equation in one-dimensional open channel flows. In the same layer, Amwari Hayat and Pipe Sheng published in the article where it was shown that in explicit quadratic Lyapunov function was considered as weight function of small perturbation of stationary states, which in turn graduates expressional stability. And other scientific we have. We can say that the problem of unsteady movement in open channel is being paid great attention, as evidenced by a number of reports, scientific works devoted most unsteady of flows. However, despite the success achieved in this area, a number of problems remain unresolved here, and little attention is paid to same areas of research. And the Saint-Venant equations can be represented in this linearization form like this one. Boundary condition we can give like the form 2, and initial condition we can give like the form 3. And here lambda 1 and lambda 2, this under the subcritical conditions, the system has a two real distinct eigenvalues. This is lambda 1 and lambda 2, and we have these parameters, gamma 1, delta 1, gamma 2, delta 2. Here, these parameters are initially given functions, and then we have give a boundary conditions parameters, and here K0, K1 RS, a parameter of boundary conditions, and which we will calculate later, this parameter. And here H with an asterisk and V with an asterisk are two stationary solutions of system of Saint-Venant equation, and where H is the water depth and V is the horizontal water velocity. Both of are unknown functions of two variables, and slope we give like this, Sx is the channel bottom slope, G is the constant gravity acceleration, and K is the constant friction coefficient. And then we will build a difference grid in the area G with the steps delta t in the direction t and the delta x and the direction x. The nodal points of the difference mesh are denoted by tk and xg. The set of nodal points of difference grid is denoted by GH, where GH we will give like this form, and this value is numerical solution of at the nodal points are denoted by like this. We select the steps of difference grid delta t and delta x in such a way that the inequalities k multiply delta t equals t and g multiply delta x equal L equal to L. Find a numerical solution to the mixed problem 1, 2, 3 over the difference grid GH. We propose the following affine difference splitting scheme for the lower terms, like form 4 and 5. This difference scheme. Boundary conditions 2 and initial conditions 3 are approximated like following way, like 6 and 7. Suppose that the steps of difference grid satisfy the current Friedrich-Levy conditions. Now let us investigate the question of the exponential stable numerical solution of difference problem 4 and 7. First, we give the definition of the exponential stability of numerical solution of the difference problem 4 and 7. Definition 1. The solution of difference scheme 4 and 5 satisfying the boundary conditions 6 is called exponentially stable if there are positive constants, two constants, such that for any initial condition in the space L2. Look this. L2, the solution of the difference initial boundary value problem 4 and 7 satisfies this inequality, where L2 is a discrete space L2, the norm of which is determined by the inequality like this, and it is limited. Consider the difference boundary value problem 4 and 6 with a stationary solution like this. In order to prove the exponential stability of the difference initial boundary value problem 4 and 7, we propose the following function of as a candidate of discrete Lyapunov function. Like this. V1, V2, U1 and U2 we give like form 9 and 10. This here parameter mu is greater than 0 and two function f1 and f2 to be determined. Lambda 1, lambda 2, it is eigenvalues. Theorem 1. Let t greater than 0 and the discrete Lyapunov function is determined using the formula and 8 and 10. If the steps of difference grid satisfy the current Friedrich conditions 8 and the parameter of boundary conditions B0 and B1 obey the inequality 11, the numerical solution of the difference initial boundary value problem 1 and 4 exponential stable in the L2 norm. To prove the theorem 1, we need some lemmas, but I don't give these lemmas because we must have much time, and now we give a numerical example. We consider a pool of prismatic open channel with the rectangular cross-section as a value of parameters of numerical example considers the following. We give a channel length, steps, time step, channel width, and stream of rate of change, and constant coefficient of friction, like this form. And then since we are considering runoff of river modes, the values H with an asterisk and V with an asterisk must correspond to the inequality, like this inequality. Only in this case, lambda 1 and lambda 2, we will take a positive value. In addition, we must not forget that equality, Taking into account the above, H with an asterisk and V with an asterisk, we have chosen as like this, and the graph of H with an asterisk and V with an asterisk, we will look like this form. Accordingly, we take lambda 1 and lambda 2 as like this form. We know that stationary states have three possible dynamics depending on the slope. In this numerical experiment, we consider the case when the G multiplies S equal to this form. This means that friction tilt and compensate each other. Then the bottom slope, we will have the form like this, S equal to this. Initial condition we give like this. Also, we will be given this parameter, gamma 1, delta 1, gamma 2, delta 2, and P1 and P2. Then to determine the numerical solution 1, 3, we use the difference splitting scheme for the lowest terms, 4 and 7. According to theorem 1, the conditions for exponential stability of the numerical solution take place in the fulfillment of the current Friedrich-Levy conditions, as well as the parameters of boundary conditions B0 and B1 must satisfy in the inequality 11. And simple calculations show that the current Friedrich-Levy condition is like this, and boundary values B0 and B1 satisfies the inequality 11. It's mean like this. Okay, and let us we give a graph of the L2 norm of the numerical solution on the figure 1. This means which confirm of exponential stability of the numerical solution to L2 norm. Okay. To numerical values of the L2 norm, the numericals of the numerical solution of the corresponding layers in the time are given in the following table. If you see, this is good result. Now we consider the case when the current Friedrich-Levy condition is not satisfied, when the greater than 1. And this case, the L2 norm of the numerical solution increase with the time, which means of instability. Numerical solution increases with the time. In this figure, we can see this. And conclusion, in this report, we have proposed an opposite difference scheme for the numerical solution of the Saint-Venant system of equation. To prove the stability of numerical solution, a discrete Lyapunov function was proposed, and theorem of stability of numerical solution was also proved, and computational experiments were carried out proving that if the condition of the theorem are met, the numerical solution will be stable under any initial condition. This is my presentation. Thank you for your attention. If you have any question, please.
Can I ask a question?
Yes, please.
Yeah. Thank you so much, Dr. Aziza, for your good presentation. Could you please tell me regarding the application of your solution in the real world?
Real world, we application for the rivers in Uzbekistan. For example, we application for the Ugam River. This is a mountain river. We solve this equation, and we 1 minute, please. We counted the water depth and for 1 minute, please.
Okay.
What? For Ugam River, we counted the water depth and the horizontal water velocity. And for, the mountain river solving is very difficult. But we do this.
Sorry, did you compare with another solution?
No.
Oh.
Only Saint-Venant equation.
Oh, sorry. And one more question. Could you please tell me how you translate this real world problem to equation 1 in a slide 1?
Slide 1.
Equation 1.
Uh-huh.
Okay. How you translate this real world to this equation?
Oh, okay. This equation, in this equation, first we'll given in the work Bastien. Bastien translate linearizate Saint-Venant equation, system of equation, non-linearized form in the linearized form, this form. In Bastien and Amari Hayat this work this. I give this form and then I solution this.
Okay. You mean there are many limitations regarding this equation because there are many variables to affect in your result. That
Yes,
you choose
yes.
only some important variables to consider in your study.
When we choose the parameters, we see which area we see.
You mean this equation is only specific for a special river that you told me the name of this.
Oh, this oh, okay. This system for a channel, rectangular cross section.
Oh, okay. Thank you. Thank you so much.
Hello. So we have a question at chat box. So let me read the question. So Dr. Aziza, can you provide an example of a software package commonly used for numerical simulation of a Saint-Venant equation from Dr. Izzati Khairudin?
Sorry, can you repeat, please?
Can you provide an example of software package commonly used for numerical simulation of a Saint-Venant equation?
Numerical simulation. Oh, okay. Right. For numerical simulation, I don't give this form. I'm sorry.
You
In this
don't understand the
presentation, we
question,
don't give.
Dr. Aziza. They're asking which software you are using in your research, solving your
Software.
yeah, software.
Okay. This is work. We will use the Matcat. Matcat, you know this Matcat, and Python. we use MathCAD. First, we will use MathCAD, then we will use Python in the Python. This.
So what's the preferability of choosing such software? Why you're choosing this software to solve?
At first, because because this is simple for work. This software, MathCAD, is very simple for work, and we use this.
Is it for all such kind problems that the software is used, or some preferability there?
Yes, it's
Say Maple or C or Mathematica. So a lot of softwares you can use in your research or in mathematical research. So why you are choosing this, namely this one, this software, MathCAD?
Yes, we can do this in a Maple, but both of software in the result is the same. Result is same, and MathCAD and other MATLAB.
Right. Thank you, Dr. Aziza, for letting us. So, is there any question? If no, we go to the next session. So, thank you again for Dr. Aziza sharing us the knowledge.
Thank
So, let's go on to next session, which is photo session. So I sincerely hope that everyone will turn on their camera for this. Okay. I hope that everyone is now prepared. So 1, 2, 3, smile. Okay. So smile. Smile. 1, 2, 3. Okay. All right. Thank you, everyone, for turning on the camera. So this is the end of our first session. We hope that the participants gain some interesting knowledge from this webinar. And please feel free to contact both speakers via their emails for further applications. Please fill in the attendance form to get your e-certificate and for 20 hours professors for your attend staff. We appreciate your attendance and the contribution of our speaker. Your presence makes us really happy. The fifth session will take place on June 16. We really hope to see you again. This session can also be watched again through our YouTube channel. Assalamualaikum. Bye.
Hi, assalamu alaikum. Hi there.